Okay, let's continue. Addition of rational numbers. Let's begin. Can we add rational numbers? So let m n be integers and not equal to 0. Let r s be integers, s not equal to 0. Now the goal is we want to define m by n plus r by s. So then m by n is the unique point box such that n times box is m. R by s is the unique point box such that s times such that s times box is r. Now the goal is we want to define this m by n plus r by s. So we want to define this box, square box plus hexagonal box. We want to define the sum of these 2 points. We want to define so this is what we want to define, box plus hexagon. Okay, so we have n times box equals m, s times hexagon equals r. Hence Sn times box equals Sm, Ns times hexagon equals Nr. And we can add the equations, adding the equations. So we get Sn box plus Ns hexagon equals Sm plus Nr. We want to define the sum of these 2 points such that we have distributivity. Right? Distributivity. We want to define box plus hexagon such that we have distributivity. So we want this property to hold. So Sn box plus Ns box, Ns hexagon. This is the LHS above. Equals, we want to define this. We want to define box plus hexagon such that we can take Sn common. Right? So we want this property to hold. In this ideal case, we have Ns times box, so you have ns times box plus hexagon equals sm plus nr, right? So this equation becomes this equation, right? ns times box plus hexagon equals sm plus nr, that is box plus hexagon equals sm plus nr by ns. So in this ideal case, we have box plus hexagon to be this rational number. Hence we define box plus hexagon is defined to be sm plus nr by ns. That is, so box is just m by n and hexagon is r by s. We define m by n plus r by s equals sm plus nr by ns. That is, so this is the definition of addition. So the above wanting distributivity of addition, so distributivity of multiplication of an integer, like note that this is an integer, sm plus box is this integer sm, ns plus box is this integer nr. So in both are integers, and this we want to define. We want to define such that the sum of these integers is ns times this point. So this addition we wanted to define in, and we saw that in this we wanted to define this addition such that this distributivity holds. Sn times box plus Sn times ns times hexagon is ns times box plus hexagon. We wanted to be able to take ns common. So in this ideal case, we have from the above equation Sn box plus ns hexagon equals Sn plus nr. From that we have this equation, ns times box plus hexagon equals sm plus nr, that is box plus hexagon is sm plus nr by ns. So what did we do? So we started with two integers m and n is not equal to 0, integers r s is not equal to 0. The goal is to define m by n plus r by s. We expressed m by n as some box and hexagon via the definition. M by n is the unique point box, as it's n times box is m, and so on. Then we wanted to define this box plus hexagon. We have these two equations defining box and hexagon. N times box is m, s times hexagon is r. We multiplied and we added, and then we wanted to define box plus hexagon such that we can take ns common out of this equation. So in this ideal case, we can take ns common out of the equation, out of the left hand side of the equation, and we can write in the ideal case box plus hexagon equals sm plus nr by ns. Hence we define box plus hexagon to be this quantity sm plus nr by ns, that is m by n plus r by s equals sm plus nr by ns. In other words, this is the main thing, m by n plus r by s, we can take sm by sn plus nr by ns. So this we define, we have the same denominator. This we define to be sm plus nr by ns. So here we have same denominator. So once we make the rational numbers to have same denominator, to add the rational numbers we just add the numerators. That's what this definition says. In other words, m by n plus r by s is sm by sn plus nr by ns, which is sm plus nr by ns. Okay, so this is how we define addition of rational numbers. Example, 3 by 5 plus 4 by 7 equals 7 times 3 by 7 times 5 plus 5 times 4 by 5 times 7 equals 7 times 3 plus 5 times 4. Once you brought both the fractions to have same denominator, we just add the numerators and to add the fractions, and we get 21 plus 20, 41 by 35. Hence 3 by 5 plus 4 by 7 equals 41 by 35. Right? So this is one example. Another example. Minus 5 by 2 plus 3 by 7 equals 7 times minus 5 by 7 times 2 plus 2 times 3 by 2 times 7. Now that the denominators are same, we just add the numerators. 2 times 3, which is minus 35 plus 6 is minus 29. So minus 29 by 14. Hence, minus 5 by 2 plus 3 by 7 is minus 29 by 14. We are just using the above definition in the box. M by n plus r by s is Sm by Sn plus Nr by Ns. The first equality is by the cancellation law. We can multiply numerator and denominator by same non-zero integer and the fraction doesn't change, the rational number doesn't change. So m by n plus r by s is Sm by Sn plus Nr by Ns. Now that we have same denominator, we define the sum of these two rational numbers to be Sm plus Nr by Ns. We just add the numerators and retain the denominator. Why did we define it like this? Because we wanted distributivity in this above analysis. Right. We wanted to be able to take. Where is the laser pointer? 1 second. Yeah. Here we wanted to be able to take in this equation. We wanted to be able to take ns common. We wanted to define box plus hexagons in such a way that we can take ns common from this term. From this expression we can take ns common. We wanted this equality to hold. Hence in this ideal case we got that we took Sn common and we wrote this equation and we found out box plus hexagon, right? So hence we define. So since we want this to if that ideal case holds, we found that the sum is of this form. Hence we define the sum to begin with to be this rational number, right? Okay, so this is how we define addition of rational numbers. So we can ask, does this addition agree with the addition of integers? So let a be integers, then a by 1 plus b by 1 equals a plus b by 1. Hence addition of rational numbers agrees with the usual addition of integers. right? So, and we can ask another question: what are the properties of addition of rationals? What are the properties of addition of rationals? So here's the observation. So we have commutativity and associativity. Addition of rationals satisfies commutativity. That is, order doesn't matter. And associativity. That is, grouping doesn't matter. So proof, first for commutativity, it's as usual, let mn be integers and not equal to 0. Let rs be integers, s not equal to 0. Now m by n plus r by s is sm by sn plus nr by ns, which is sm plus nr by ns, and r by s plus m by n equals nr by ns plus sm by sn. This is nr plus sm by ns, and both the quantities, they are equal. Hence order doesn't matter. That is, m by n plus r by s, these two sums are equal, right? So addition is commutative. Commutativity we showed. We are left to show associativity. So for associativity, right, we need to take three rational numbers, right? Let mn be integers and not equal to 0. Let pq be integers, q not equal to 0. Let rs be integers, s not equal to 0. Then, so if we take m by n plus p by q plus r by s, so this is m by n plus sp plus qr by qs, right? If we take common denominator, right? And then this is in turn qsm by qsn plus n times sp plus qr by n times qs. So this is qsm plus n times sp plus qr by nqs. This is the first sum, m by n plus p by q plus r by s. Also, if we take m by n plus p by q first, m by n plus p by q plus r by s, this is qm by qn plus np by nq. So qm plus np by nq, right? And plus r by s. So this again is s times qm plus np by s and q plus nq times r by nq times s. So this is s times qm plus np plus nqr by nqs. Now note that this quantity and this quantity, so sqm plus snp plus nqr, so numerators are same and denominators are same. These two quantities are equal, right? So these two quantities are equal, hence m by n plus, if we add p by q plus r by s first, or if we add m by n plus p by q first, we get the same result in this sum. Okay, so grouping doesn't matter. So addition of rationals satisfies commutativity, that is order doesn't matter, and associativity that is grouping doesn't matter, right? So we showed this two properties, and right, that's all for this part. See you in the next part.